Question 8. An object of mass 60 kilograms is on a rough plane inclined at an angle of 20 degrees to the horizontal. The coefficient of friction between the object and the plane is 0.3. Initially, the object is held at rest. A force which is parallel to the plane and of magnitude T newtons is applied to the object in an upward direction along the line of greatest slope. The object is then released. Given that t is equal to 15, calculate the acceleration of the object down the plane. Question says it is a rough plane, so we know that there is friction involved, and it also tells us the coefficient of friction between the object and the plane. The question also says that t is acting in an upward direction along the line of greatest slope. It also tells us when t is 15 we have to calculate the acceleration down the plane, so we know it is accelerating down the plane. So let's move on and look at a diagram of the situation. So we have a diagram with a mass of 60 kilograms, so it has a weight of 60 g acting vertically downwards. It is on the plane, so there's a normal reaction which we've marked as R. The force of T, which is 15, is up the plane, but we know the movement is down the plane, and so friction opposes the movement, so friction is up. So at the minute we've got a diagram like this, but we know any movement is up or down the plane. So we want all forces either parallel to the plane or perpendicular to the plane. So what we're going to do first is look at the 60g component forces, which are perpendicular to the plane and parallel to the plane, and put those in. So the weight 60g downwards will have a weight component 60g cos 20 perpendicular to the plane, and a weight component 60g sin 20 parallel to the plane. And we know that the acceleration is down the plane. So now all our forces are either parallel to the plane or perpendicular to the plane. Now, if we think perpendicular to the plane, these forces must balance, because it won't move off through the air, it won't move down through the plane in any way, it can only move along the plane. So these forces must balance. So R must equal 60g cos 20 when we resolve perpendicular to the plane. So we've got some fact here which helps us with R. We need to know R because there is friction, but the friction must be the maximum friction because we know it's moving down the plane, so it's used all the potential friction it has to try and stop it moving down the plane. So we will be thinking that F equals mu R is the maximum friction. So the friction force, which you've said is maximum, which is mu R, is 0.3 times R, but we know R is 60g cos 20. If we type that in, we get the friction force is 165.76. If we now consider parallel to the plane and think about Newton's second law, which is force equals mass times acceleration, we know the acceleration is down the plane. We know the mass is 60, and we want to know what force is helping this acceleration. So the 60g sin 20 is helping the acceleration. The 15 and the frictional force are opposing this motion, so we can look at that in our equation. So M was 60, the acceleration is what we're finding, and the resultant force down the plane is the 60g sine 20 minus the 15 and minus F, which is 165.76. So if we divide all of this by 60, we get the acceleration is 0.3391 meters per second per second. So if we move on to part B, given that t is 350, determine whether or not the object moves up the plane. Give a reason for your answer. So the diagram, the weight is 60g, so we've still got its component 60g cos 20, 60g sine 20. It's still a normal reaction perpendicular to the plane, and it says tractive force up the plane is 350 newtons, so we put that on the diagram. And the question also asks whether or not the object moves up the plane, so we can know that in this case the friction is acting down. So if we put that on the diagram, so let's think about 60g sine 20 and evaluate that. So 60 times 9.8 times sine 20, and we get 201.11. If we'd resolved perpendicular to the plane, everything must balance there, so R should equal 60g cos 20 the maximum friction is still 165.76. So if we look at the situation, there is a force of 350 upwards, there is a force of 201.11 downwards, and there is 165.76 newtons of friction available to try and stop it moving up. But we notice if we look at the 201.11 and the 165.76 and add those together, we get 366.87, so that total force is bigger than the 350, so it will not move up the plane. The frictional force is actually 148.89, because if we add that to the 201.11, we get the 350 newtons, which is up, and the 350, which is down, and so there is no motion. So it is used 148.89 of its potential friction of 165.76 to stop any movement.
One of the tricky bits in this question is the resolving of the 60g force into two components. So I'm just going to have a little look at that. So we'll start off with a basic diagram. We'll also extend the force down to the floor in the situation, and then we'll put a perpendicular to the slope from that point. Now in the larger triangle there we have 70 degrees at the top there, because we have a right angle at the bottom, and that means that angle there is 20 degrees, and chasing these angles round to make sure they're the right way round is very important. So it's worth doing it carefully if you're not 100% on top of this aspect of these questions. So we've now got that right angle triangle there. Both components act from the same point as the original force, so they look like that. But if we put a dotted line across there, so that's parallel to the plane, then that length I've just added dots to is the same length as our perpendicular force. So now we'll give these two components names. So that one we'll call F parallel, that one F perpendicular, and then we can draw a triangle separate from the diagram to represent the situation. Now F parallel is next to the 70-degree angle, and the original force that we are making into components also is next to the 70-degree angle. So that means F parallel must go there, and the 60G force is the hypotenuse, and of course the perpendicular force must then go there. We have 20 degrees down the bottom, and we of course have a right angle, which I haven't put in, but it's implicit. So we've got an ordinary right angle triangle. The parallel force is opposite the 20 degrees, so we can say that F parallel over 60G is sine of 20, and therefore F parallel equals 60G sine 20. F perpendicular is the adjacent, so that will give us cos 20 degrees, and therefore the parallel force is 60G cos 20. Now, it's obviously crucial to get these forces right, and it's very easy to slip up. So, unless you're very fluent, and even if you're quite fluent, you might benefit from very carefully putting on the diagram what I've put on there, or something similar that suits you. And you also may well benefit from making a separate diagram to make absolutely sure of this. The point being that unless you get these two forces right, then not only will you lose marks for that bit of the question, the consequence of having those numbers wrong may be that in a question like this, where you're looking at whether frictional forces will be strong enough to stop movement or will allow movement, then if some of the numbers change dramatically, then you'll end up with situations quite different from the question, which may even mean you're not even able to pick up some follow-on marks with your incorrect work. So practice this and make sure that you're fluent in doing these diagrams. At some point you may get to the point where you don't need to anymore, which is fine.
Let's look at a new problem that is not on that question, but let's imagine that a force of 50 newtons was acting down the plane, so the object was being pulled down the plane, and we're going to say that the plane is now made rougher, so the coefficient of friction is 0.5. We know that R is still 60G cos 20, so the maximum friction will be mu R, which will be 0.5 times 60G cos 20. This is 276.3 newtons, and if we look here, there is a weight component 201.11 and 50 here, which gives us 251.11 in total, but the friction will be the 251.11 to oppose that, but its potential friction is 276.3, but it doesn't need to use it all, so it actually uses 261.11 newtons of friction. If we now change this force down to 100, there would still be a 201.11 weight component, the maximum friction would be 276.3, but the 100 and the 201.11 is 301.11, which is more than the 276.3. So it would accelerate downwards and it would use the maximum friction.